Hi, this is Getting Data In and Out of Earth Engine, and I'm Alex Morose. I'm a senior software engineer at Google Research.
I'm Michael DeWitt. I'm a developer relations engineer on the Earth Engine team.
Hi, I'm Sam. I'm the creator of the awesome G community catalog and a Google developer expert.
Hi, I'm Gino Michelli. I'm also a developer relations engineer on the Google Earth Engine team. Welcome. Well, thank you, everyone, for joining us. Again, this is getting your data into and out of Earth Engine. So today we're going to be talking to you about a couple of core concepts just to lay the groundwork so you understand all the terminology that we'll be using and more specifically what we mean when we say different terms. Logically, the talk is roughly divided into getting data into Earth Engine and getting data out of Earth Engine, as one would expect. And then we have a section on some power tools, some advanced tools that are open source on GitHub that you can use to do even more execute more powerful workflows. Right, so without further ado, we'll start with some core concepts. For many of you, this may be review. If you're familiar with Earth Engine already, you'll know that there is a data catalog, which is Google Earth Engine's public data archive, which contains over 80 petabytes of publicly accessible information through Earth Engine. That catalog is managed by Google. That is the data catalog. So today we're primarily not talking about getting data into the Earth Engine catalog. We'll be talking more about what you can do with your own assets. Okay, so assets are your user data. This data can be private, or you can share it with others. You control who sees that data. There is a default quota that you can get. There's uplift. There's commercial pricing for different amounts, and you can get up to 10,000 assets with your default account. Just talking about assets, there are primarily 3 different types of assets in your Earth Engine asset storage. The first is the obvious one, the image, which is a single raster image, so a grid of pixels, which may have one or more bands. So if you're a remote sensing or GIS specialist, you'll understand this very well, like red, green, blue, infrared. And then each image can have a set of properties. So there'll be some metadata about the image with capture date, how it was captured, the source, an index. But rarely do you need to work with only one image in your workflows. You'll very often need to work with lots of images together. In that case, we have what's called an image collection. So when we say an image collection, we're referring to a primitive type inside of Earth Engine that it understands how to index so that when you perform your operations like filtering and aggregation, they can be performed efficiently. Lastly, we talk about tables, which in Earth Engine code was called a feature collection. And that is essentially the vector data type of Earth Engine, a collection of geometries on a map. If you create a feature collection, there's a geometry column which gets inferred when you're importing a table from a table. The other columns get used as properties of those features on the map. So for all of these different elements in Earth Engine, they can have associated with them metadata, which we call properties. So next, just to quickly disambiguate when we're talking about ingestion into Earth Engine versus registration of data with Earth Engine. So when we say data ingestion, we've hired 10,000 cats to actually take all of your data and shove them into, no, just kidding. There's the automated process of taking data and pre-processing it, pre-indexing it, referencing it, and storing it in our internal format. This takes time, okay? You get faster analysis out of this, but you have to first import the data into Earth Engine, or as we say, upload the data. The data registration, the data doesn't actually never gets ingested into Earth Engine, as you see this slightly sad cat here realizing. In this case, we tell Earth Engine about the existence of this data. So currently, that means cloud-optimized GeoTIFFs living somewhere on Google Cloud Storage. That's much faster to get working because you can just register your asset with Earth Engine, and it doesn't get ingested. The downside is that there's much slower analysis because it isn't pre-indexed and pre-processed to be optimized for use with Earth Engine. We'll get to that. We'll get back to that later in Sam's talk. The next thing I want to just disambiguate is the difference between export versus extraction. These can be considered also made-up terms, but we are trying to define them very clearly so that way, it's not entirely arbitrary, that we want to have clear definitions of things when we talk about them. So when we say data export, we're talking about using Earth Engine's built-in export APIs, export.image, export.table, to kick off an export task, which happens asynchronously. And at some point in the future, the data then appears in cloud storage, Drive, BigQuery. This uses a different bit of infrastructure in Earth Engine called the batch processor. So it uses a different type of quota in a different environment. These tend to be long-running processes. It takes approximately 1 minute to start up one of these batch processes and 1 minute to tear it down. So you're looking at a minimum of 2 minutes to export data this way. So this is when you have large data sets that you just want to point to a storage location, let it do its thing, and come back later and access the data. The state of these export processes is visible in the code editor through the task manager. The second thing that we've recently dubbed data extraction. When we're saying data extraction, we're talking about actually pulling pixels out of Earth Engine synchronously, meaning your code calls Earth Engine and says, give me these pixels for this area, and I want them right now. I don't want to go back and look someplace else for them afterwards. This uses a different processor, the interactive processing pipeline, and it consumes a different type of quota. The benefit of this is that there's lower latency than actual export, but you have to manage the calls to get pixels and to compute pixels, the functions you'll see later that do this yourself. This method can also leverage our high volume API and also uplifts that can help you scale your processes. So if you want to parallelize a part of your workflow on your own, this is how you would do it. Right, so now I'm going to pass you to Sam to talk about getting data into Earth Engine. Thank you.
Thank you, Gina. Hello, everyone. We're going to talk a little bit about getting data in. This is one of the primary things that most of you worry about when you're discussing two types of mechanics, right? Like, oh, you have a lot of data that's sitting on your local drives, that are sitting on an FTP server, that is sitting on a zip file somewhere. Or you have these data sets that are on cloud storage, but you don't necessarily know what to do with them. You kind of wish they were in Google Earth Engine, but they're not. So my talk is going to be focusing on getting data in. I'm going to be going over concepts like cloud-optimized GeoTIFFs, because you might have heard of them, but you don't necessarily know what to do with them. I'll be showing you what exactly does it mean when we talk about data registration versus ingestion. And I'm also going to talk about a little bit about strategies when you talk about getting data in. OK, so one of the primary ways of getting data in is the code editor assets, right? And if you think about the fact that every time you're given an Earth Engine project, when you import a new Google Cloud project, you're given 250 gigabytes of space, and you're given about 50,000 assets that come. The 50,000 assets piece is just a count of how many assets you put into your project. And 250 gigabytes is the max limit. Of course, if you need more for research, there is a quota uplift form that you can fill to get additional quota. But let's imagine for a minute that you did not have that limit, right? And you're not worried about the 250 gigabytes. Here are some basic limitations of the code editor assets themselves. You cannot upload a file that's more than 10 gig right now. This was designed because it's a browser and there might be stability issues. As you actually click on the Assets tab and click on the Upload Data, what really happens is Earth Engine generates an upload URL. And when you actually click on your file, it piecemeals your data and sends it to an Earth Engine service. Then a worker is allocated, and that worker takes all of those chunks together, synchronizes them, converts it into whatever format Earth Engine might need it, and then it makes the ingest queue actually starts. That's the reason you'll say, uploading, do not close your browser. Do not close your browser, because it's genuinely uploading. So it is heavily reliant on your upload speed. So that's the one thing that you have to keep in mind. And that's irrelevant of whether this is in code editor or whether this is something you're doing programmatically. If your data is local, it will depend on your upload speed if you're ingesting. The next thing is, you might have seen this if you work in the Python environment and if you're using the command line tool. The command line tool has a couple of tools, and some of these include the upload and upload manifest. The upload tool is simply that, hey, I have this data set. It's a GeoTIFF file that's sitting on Google Cloud somewhere, a Google Cloud bucket. I have access to that Google Cloud bucket, and now I want to ingest it. The good news is that you can do this. Your GeoTIFFs don't have to be cloud-optimized GeoTIFFs. It can be any kind of GeoTIFF as long as it has projection and it's properly formatted. You should be able to ingest it as long as you are the owner of that bucket or you have read permissions to that bucket, and Earth Engine can also read that bucket. So your cloud permissions have to be configured enough to be able to read that. The upload manifest, I believe, will be the one in which you'll be able to bring in a manifest file, and we'll get into that a little bit. So there is actually a comparison between the code editor and command line tools. So some of the things that you can do in code editor is create folders and move, rename assets, monitor assets. You can do most of these things. In fact, you can do all of these things in code editor. In the command line tool, you can do some specific things like upload with manifest. And whenever you hear the word manifest, think of the manifest as a way of organizing what are the information that Earth Engine needs to have to arrange your data. So imagine you're giving your data to Earth Engine, and you have 2 bands. And you don't want Earth Engine to automatically allocate the band names as B1 and B2. You want to actually call it that the first band is temperature, and the second one is, let's say, I don't know, like air pressure or something like that. And you really want to pass that to Earth Engine, you can do that in a manifest. You also want to give it a time start because you want to be able to filter this. It's a lot of images. You want to filter it by date and stuff. You want to give that here as well. Now you can do this in code editor. By the way, the code editor actually uses a manifest in the backend to make all of this possible. That's how the code editor actually is functioning. So a manifest is a nice way of arranging all of this information, including adding properties. You have a version number. You have a license text that you want to pass. You want to pass a URL that people can reference the base data from, right? All of this can go into a manifest, and it's a neat way of telling Earth Engine, this is where my data is, now go ingest it. Nothing else changes, okay? So uploading from CLI with manifest, again, this is just an example. By the way, there's a Qwiklabs link, so once this presentation becomes available, people can go try this. You can also try this locally on your machine if you want to, and if you already have the Earth Engine CLI installed, where you're able to authenticate. There's a manifest example there, and it'll show you how to arrange the path to your Google Cloud Storage asset or the TIFF file. Yeah? And then you can also give it a path to your asset ID. Remember one thing, that if you are ingesting and you have a folder inside a folder inside a folder, you have to make sure that those subfolders actually exist. These operations will not make those nested folders for you. So you have to make sure that those nested folders or collections actually exist. Otherwise, it doesn't have a place to write to. Again, data ingestion API. So what actually it does is once it collects all this information, right, you give it a manifest and you basically pass it to Earth Engine. You are telling Earth Engine to then allocate a worker. And whenever I use the word worker, think of this as analogous to you're seeing the task ID. You're used to seeing a task running, and you have the task ID running. Think of all of those task IDs as tiny little workers that are doing work in the backend, right? So when you start your ingest job, task ID is allocated to your ingest process, and that's when it starts churning, and in the backend, it's actually ingesting a lot of data to your Earth Engine. There are some caveats here. If you're doing a lot of ingest, at any given time, you will have approximately 5 to 10 ingests running. That really varies, and if you're lucky, you'll have more. If you're really unlucky and Earth Engine is overloaded because everyone is using Earth Engine, you might get less workers. So not all tasks will start simultaneously. Your maximum queue length is 3,000, which means if you have more than 3,000 objects, if you say, I want to start all these processes together, you will submit all of this, but after 3,000, Earth Engine won't even let you submit any more task requests. So you have to wait for a little bit, so some of your tasks are completed, and then you can make more requests as needed. The other two ways of getting data into Earth Engine are pretty standard, but I want to talk about the main one is, yes, you can go to the link that's mentioned here. You can get data into data catalog by requesting it to the data catalogs team. So this is monitored by Simon and team, so when you request it, and people can go and star it or thumbs up it, and basically that's your way of voting and saying, I really think that this data is important for the community. We want this to be made available. I wanted to shamelessly plug this in. Apart from going through the master catalog, if you are a researcher and if you have some data that you want to be inputted in, and you know that, okay, Simon and team have a lot of large data sets that they're already working on, they don't have the bandwidth maybe, and you really need this data set for whatever you're doing, you can also submit a request to the Google Earth Engine Community Catalog, which I monitor, and I might be able to get that data in faster, depending on how large your data set request is. Cannot be like 25 terabytes or something. Okay, the next thing we're going to talk about is just a little bit about COGS. And you'll hear this a lot of times because there's a couple of operations that were introduced into Earth Engine gradually about COGS. One of them was the fact that you could read directly cloud-optimized GeoTIFF that's sitting on a Google Cloud Storage bucket. And let me repeat that. That COG, that cloud-optimized GeoTIFF, has to be sitting on a Google Cloud Storage bucket. It can't be on any other cloud provider. It has to be the Google Cloud provider. So COGs are popular. They are useful because you can make range reads to COGs, which means that you can just request a part of a COG rather than requesting the entire TIFF file, right? So you can just go and say, I need this northwest corner, and you can basically give it a window and say, okay, I'm going to make this HTTP request, and it'll only give you that piece. That makes it really, really useful because you have kind of indexed the whole imagery, and you can request a portion of the imagery rather than getting the whole imagery. Really useful, really nice, right? And it's like store in GCS, read in Earth Engine. This is the common flow. This is what was introduced initially, right? That you store a Google Cloud Storage, you store a GeoTIFF, a cloud-optimized GeoTIFF in a Google Cloud Storage bucket, and then you tell Earth Engine, hey, can you go read this? And it turns out that it can read it, depending on how your COG is configured. Please make sure your COG has overviews. I cannot stress this enough. It is possible for people to create COGs without overviews. Earth Engine does not generate overviews on the fly. So if you don't have overviews in your COGs, and if you're trying to use the load COG from URL feature, it will be slow, it'll struggle, there will be failures. So just make sure that there are overviews in your COGs. Pros, you can get your data immediately without import. One of the largest features of this is, you remember the 250 gigabytes limit that I said? You don't have that limit anymore. Because you can basically store terabytes of data on your Google Cloud Storage bucket. Of course, you have to pay for it. I'm not saying it's free. But you have to pay for it. But you can store hundreds of gigabytes or terabytes of data in your Google Cloud Storage bucket, and then you can read them. The limit you still have is if you're not reading but registering them. You remember the 50,000 asset count that I said? That is still counted when you register COGs. So you're still limited by it, but it's a number that is easy enough for people to upgrade you. Like if you make a request nicely and say hey, I need this for these purposes, I have 1 million assets that I want to upload, sure, you can request for a bump in your number of assets count. Rather than the 50,000, you want more, right? Cons, it can be several times slower than native assets. COGs are exactly what Gino said. They're links to where the data is. They're pointers, right? Which means that if I have a collection that has 20,000 COGs, and I say load the entire 20,000 COGs on the screen, and I zoom really out, it's going to make all of those as REST endpoints request to the bucket and say, can I get this? Can I get this? So it'll try to make all of these calls, and there might be some sluggishness. Now, I'm not saying that it's noticeable all the time. If you have a small enough collection, you may not even notice it. It might be really small. But it is a possibility that there'll be some sluggishness, so that's one of the cons. Buckets needs to be close to EE data centers. It's always nice when there's co-location of where you're reading the bucket from and where the Earth Engine actually is. Pyramiding overviews need to be done correctly. And that part is important because, like I said, it doesn't do pyramiding or overviews on the fly. So you're not going to have any luck if you don't have pyramids generated. Using COGS. Again, the load GeoTIFF method is the easiest way of loading a GeoTIFF. So you can actually give it multiple URLs, and you can also create like, in here, it basically, in the small snippet example that you're seeing, you will notice that it basically has the pathways for more than one tag. I think more than one TIFF file, or maybe it's a very long path. I think it can currently load a single TIFF file, and correct me if I'm wrong on that. Can it load more than a single TIFF file, the load GeoTIFF? Okay. It can only load a single TIFF file. I was wrong. If you want to do more than a single TIFF file, register them as collections. The COGBit assets that's exactly what it is. So you can basically create an image collection that'll have an effective size of 0, but you'll still get the assets registered to them. And just to give you all a hint of what that looks like, I'm going to create a COG-based collection for you. And I'm going to show you what that looks like, what it feels like, why it's useful, may not be useful, and so on. Again, there is a Colab notebook that's going to be available to you after the presentation, so you can also try this yourself if you have some COGs already in your cloud storage bucket. Okay. Can we switch to the live demo, please? So cloud-optimized GeoTIFFs are really, really useful, specifically because if you're constrained on the fact that, hey, I want to create a new Google Cloud project, I don't want to deal with submitting a request form, and also that request form isn't really for everybody, so it's not really like something that everybody can say that I want 100 terabyte additional quota. It just doesn't work that way. I've tried. So if you really wanted to actually think about like getting data sets from COGS, right, you can basically look at all of the collections that you have on your cloud-optimized GeoTIFF buckets, and let's say that you have some collections, and I have some collections, and I'm going to show you all an example. Now, for this demo, and from this day forward, I actually built a tool for anyone who wants to basically register a number of COGs that you have in buckets. It's called COGEE. You can just point it at a bucket, and you can give it a prefix or a subfolder name if you have one. You can point it at an Earth Engine collection. As long as you have permissions configured on both sides, which means it can read the bucket and it can write to Earth Engine, you'll be able to directly write a collection onto Earth Engine from all your COGs. And it's really fast because the one cool thing about COG registration is that unlike ingestion, it does not need a task ID. It's no batch workers, no task queues, none of that. Okay. So what I'm going to do is I have some data set that's in this collection called COGEE. Yeah, I should have named it something else. But beside the point, so I'm going to basically show you all that. Let's say I actually want to use the tool to list all this, right? So I can actually go and say, COGEE, give me my buckets right now. And that's OK. You can look at my buckets. None of these are public, so. It basically goes in and tells me what are all my buckets right now to which I have permissions. And I can play around with this as much as I wanted to. I can also look at like sub-buckets if I wanted to do a recursive. So if I wanted to like say, like, hey, I don't know, let's say within COG public or something. OK, let's say COG, not buckets, but recursive. Sorry, I cannot type today. Oh, my God. Yeah. And I give it a bucket. If there is something in there, and I don't know if there's anything in there, I do not remember, then it'll usually print the sub-buckets or subfolders. OK, so there is something in there, and it fetched it, and it showed the sub-bucket or the subfolder that's inside that bucket. Sorry, my bad. That would be considered as prefix if you're using this for any of the calls. So what I'm going to do right now is I'm going to basically go back to that call that I already had pre-populated, and I'm going to tell you what I'm going to do. OK, there you go. Nope. OK, there you go. So I have what do you call cloud assets. So I have these cloud assets configured. So I have a cloud project called GEE up down. Again, not great at naming things, clearly. I can actually create a collection here, And what I'm going to do is I'm going to register some of the assets I have in this folder called COGEE. So it's a bucket which has some cloud-optimized GeoTIFFs. I have the option of choosing a limit. The reason I'm choosing a limit is only because I want to do this demo. If I wasn't choosing a limit, I think it has like 800 plus objects, and I don't want to register all of them. But what will happen is it'll basically register all of them. So I'm going to just delete this because the project is called GEE-up-down. So, okay. And I'm going to run this. And you'll notice here, the only thing I'm giving it is a bucket name and a collection name, and I'm telling it register 25 assets. Hopefully this works. So this tool, if the collection does not exist, it'll go ahead and create it, and then it'll start registering the objects. So it is actually registering, and just to prove that this is not just fancy command line work, I'm just going to refresh this, and now you'll notice that there is a new collection called calibration. Here's the fun fact. If I click on the collection, notice the file size. It says 0 bytes. Awesome, right? This is because it's not actually ingesting any data. It's just pointing to that data. That's what the beauty of COGEE is. But I can actually import it, and I can use it. So I can just say, hey, let's print image collection, and let's just run this. And you'll notice that it'll give me the 25 images that were registered. It'll also tell me the number of bands. One interesting thing. Because you didn't pass a manifest, and there is no way for us to pass a manifest yet to COG objects, all band names start with a B0. This is one of those things. Just keep in mind. You can obviously rename it in script, so don't worry about that. And the other thing is, let's just center it to the first. And let's just add layer. Again, I'm hoping I had pyramids. And now it may not be the most interesting image. Okay, first of all, I'm going to stretch this so that you can actually see what exists in here. Maybe it wasn't that interesting to begin with, but we'll try. I think it was like a land cover class or something, and there isn't really multiple classes here. That's why it's just a dark image. Trust me when I say this works on other pieces of imagery. This is probably not the best collection to show you that it works on any kind of COG collection. But this is the entire process of COG registration. What it's doing in the backend, and you can go through the code, it's completely open source. What's going in the backend is it's basically registering. It's taking that path, it's registering. And one of the things I sneakishly added into this, because it doesn't give you a size, right? Sometimes you might wonder, what exactly is the size of this collection? So I actually used the Cloud Storage API to create this property called file size. And here's a really fun thing you can do. You can actually go in and say image collection dot aggregate array. No, wait, sum? Yeah. And I can actually just say file size bytes. And if I run that, it should give me the total file size of the entire collection in bytes. And you can just go to bytes to gigabytes or something. And it gives you an estimated size of what that collection actually is. Now, this is an extra thing I added. This is part of the COGEE tool. It's not part of Earth Engine Direct. But yeah, that's mostly what it is in terms of what I wanted to show you. Can we go back to the slides, please? OK, and this is getting data out. So I'm going to hand it back to Gino.
Thank you, Sam. Excellent. So I'm briefly going to introduce the second part of the segment, getting data out, and talk a bit more about export and extraction. So on the export side, you might be probably all familiar with these API calls. The primary way of exporting data is through the Earth Engine API. You'll notice on the right side of the screen, that's where in the docs you can find the different export functions. I won't read this table to you, but you can see that you have the possibility of exporting rasters to an asset, or vectors to an asset, to cloud storage, to Google Drive. You can freeze a vector data set as a feature view for high performance visualization. And most recently, you can export tables to BigQuery as well. Export is supported in a number of formats depending on what kind of data you're writing to. So I encourage you to check out the API docs, which go into detail in all of these. The most recent addition to getting data out beyond export, is data extraction. There's a Qwiklabs notebook linked in this deck, which you can get from the agenda on the G4G website. And this will show you an example of using compute pixels to compute data in Earth Engine and actually pull the data directly into your own Python script. The process of extraction and parallelization and scaling up can get quite complex. So to talk to you a little bit about navigating that complexity is Michael DeWitt.
Hello again, everyone. All right, my name is Michael. I have seen you all here before. You've seen me, but I haven't really introduced myself. So I'm Michael. I have been on the Earth Engine team for a little more than 10 years as an engineer, building out pieces of the complexity. First as a software engineer, so actually constructing algorithms and data processing pipeline pieces, ingesting new images, building new front ends, et cetera. So responsible for creating some of the complexity. And secondly, I'm now a developer relations engineer. So I'm responsible for teaching folks like you all how to navigate the complexity. Sort of a cosmic punishment. No, it's fun. I have taught thousands of people like you all how to use Earth Engine, how to get a hold of the tools, how to turn pixels into knowledge. And the best tool I have for doing that is this advice. Just read the docs. We have tons and tons of documentation on all the things we're talking about today. I am gonna share some statistics, some mental models, but the best place to look is in the Earth Engine documentation. We detail all of the numbers and the specific behaviors, the default quotas. There won't be a test. You're not expected to remember all of the different pieces here. Our goal is for you to leave with a pretty good mental model, the ability to make decisions about which pieces you want to use and how they fit into your workflows, your pipelines, et cetera. So we're done. No, we're not done. So we've talked about batch and high volume and interactive environments for Earth Engine. These are the three sort of pillars that we think about when users are interacting with Earth Engine. They're a little tricky to think about. I'm going to talk through how I think about them, how you should expect to use them if you have particular use cases, and then sort of work with some analogies on how you can model them, how you can weigh using one or the other. The documentation that I would love for you to read is, it's a page called Processing Environments. We didn't know what else to call it. We call these respectively, like we call them stacks. We have the interactive stack, the batch stack. You'll sometimes hear us refer to the online environment or the offline environment. These are just different terms that we have for talking about the different pieces of Earth Engine. So digging in, the interactive environment. This is where most application development happens. This is, we call it a synchronous stack. And so what that means is that for every request that you make, you wait and you get a response back. So if you're in the code editor or you're in an Earth Engine application and you're zooming in and you're panning around and you see those little square tiles loading in, each of those tiles is served by this interactive stack, and they're a synchronous request. So your browser is sitting there, and it sends out an HTTP request, and it gets back information, and it waits until it gets that information back. This stack is optimized for low latency because it's powering applications with people behind them. So if you have people, if you have users, human users, that are looking at a screen, waiting for a number, waiting for a map tile, waiting for any kind of result, that's an example of where you would use the interactive environment. And so this mechanism of getting data out, regardless of which specific functions you're using, the interactive environment is where you're getting those results directly. Like I said, this is typically for like web services. You can use this for integrating Earth Engine into your existing applications, existing systems. If you're building a really cool mobile application that pulls data and serves up results and polygons, hey, here's a risk of wildfire in your area, this is where you want to be. You can use the JavaScript, Python, or REST APIs, the client libraries in JavaScript or Python, to talk to the interactive stack. So phrase your questions, send them out, get responses back, and typically do that many times in a low latency kind of way. I'm so used to asking about questions. We'll have questions at the end. So if you have like burning questions, write them down. The batch environment. Batch is completely differently shaped. So we talked about data ingestion, waiting for large tasks to get in. We mentioned some limits around those tasks and the idea of scheduling tasks, and there's a queue. The batch environment is designed to move a lot of information out of Earth Engine, or for processes that take a really long time, even if at the end there's only a number. Batch is different because it is not an interactive, I send a request, I get a result. It is shaped like I send a request, and it runs in the background. And my result is put somewhere else, whether it's, like Gino pointed out, an asset, whether it's a file in cloud storage, whether it's a table in BigQuery. Sending a small instruction, a little set of instructions, hey, go export this thing, and run for a long time, and move a bunch of data in the process. When you want to create global artifacts, when you want to publish a paper, global surface water paper, global tree cover, global intertidal areas, this is the tool that you use for doing massive data movement and really long-running computations. You can see in the picture here, this particular batch job or even set of batch jobs used a lot of resources. This is a key to getting access to a lot of resources in Earth Engine. I mentioned the process of sort of handing off, describing my request, having it run, and getting the results somewhere else. There is this a little more complexity than that. So tasks go through this life cycle of being first unsubmitted. So your client, your web page, usually the code editor, is still building that description and sending it off, firing it off to where it will be broken up, analyzed, distributed across a lot of machines. I won't read all the states, but they can succeed. Hopefully they succeed. Sometimes they can fail. You can cancel them, but they are long-running things. Like we said before, they take usually a minute to start up, sometimes longer. And what that means is that it is, in starting up, we are gathering a bunch of machines, gathering a bunch of workers and resources to distribute that problem across. So if I'm exporting a large forest data set, I might need tens of workers, hundreds of workers to distribute and work in parallel across multiple days of processing. Each task has an ID. Those sort of strings of characters, please share those IDs if you have bugs or questions. It's helpful because it's a pointer exactly to that task. If you want to look at a task's status, you can use any of the tools in Earth Engine, the command line tool. You can usually look in the code editor to see the status and the current execution state of a batch task. Then we have the high volume environment. This one's tricky to talk about. This is a lot like the online interactive environment in that every request gets a response, and you are making one request per response, and they're interactive. You're waiting on the responses to come back. The difference with the high volume API is that it's designed for programmatic access and programmatic scale. So really, this is the environment. If I'm building a utility that a human is not driving, but a machine is driving, or a pipeline is driving, or a process, or a service account, a robot account, those configurations are really where you should be using the high volume API. So the high volume API is designed for that interactive set requests, but it's not optimized for latency. It's optimized for throughput. And so if you want to move a lot of pixels, a lot of information out of Earth Engine in a really scalable way, this is a tool you can use. And I see some head scratching. Isn't that what batch is for? We want to move a lot of data. The distinction really is batch is like a bus. Like running batch tasks, it's very scalable, but it is packaged up. It's a safe environment. You're not going to flip the bus unless you're doing something really crazy. High volume's a lot more like a motorcycle. Like it's up to you to get performance out of it, but you can go really, really fast. And so I'm a big fan of bad analogies. It's not the only set that we'll have today. But just the cost, the difficulty, the challenge with the high volume API is that you're the one responsible for really getting the most parallelism out of it. So you need to have a system set up to extract information, which is different from batch, where I describe the work to happen, and it magically happens in the background. And there's this great blog post from Noel about configuring faster downloads. So if you have a batch task whose performance you're unhappy with, hop on the motorcycle and try out the faster downloads blog post. Okay, yeah, I warned you. There are plenty of analogies. I'm going to do like 10 bad analogies, and then maybe you'll have a clearer picture. Or maybe it'll be much more confused. Batch and high volume, batch and interactive. If there's still confusion about when you use batch versus when you use the interactive stack, we joke about this kind of being like the difference between going to a buffet and getting table service, where a waiter or server will bring you food. Why does this make sense? So a buffet is I'm going and I am taking my plate, I'm going to get food. You all did it today. I get food, I go back, I eat. If I'm hungry again, I go back, I eat. Versus the table service, where I describe what I want to have happen, and I can get a lot brought to my table all at once. I can order 50 dishes, and they'll bring me a lot of food. We're going to keep rolling with this analogy. So quotas. Of course, there are quotas on how much you can send, how many requests you can make per unit time, how many requests you can make in parallel. There is a whole page on quotas in our documentation. I encourage you to read it. I'm going to say a lot of numbers. I'll get 80% of them right. Quotas are adjustable in some cases. So there are some numbers that are hard numbers. You can have 3,000 batch tasks pending at the same time. That's a hard number. We don't change that. That's a built-in feature of the system. But some quotas are adjustable. So you can, for example, get more parallelism out of Earth Engine, send more requests at once. You can have a higher rate of requests. So for each outstanding request, you can make more per unit time. The number of batch tasks is also, we call it uplift. You can get more access to more batch tasks running at the same time. But just know that these quota limits exist, and some of them are hard, some of them are soft. Check the documentation for the exact numbers. Yeah, this is a big source of questions in our world, is how does this work? How do I get more? There's nice docs on that. We're working with bad analogies today. This one's even shakier. So trying to describe high volume, there's a persistent confusion around the high volume stack. And it's related to how lots of folks think they want more QPS, more queries per second to make to the high volume stack. You have, let's say, a number of workers. You want to have all of those workers pulling data, and you want them to go faster. You want to get your data out faster. It is actually not usually the case that you need more queries per second, more requests per second. That rate usually isn't the thing limiting you. Usually the thing limiting you in this buffet analogy is not how fast you can run back and forth, go to the buffet, get food, go back to your table, eat, run back and forth. The thing that's limiting you is the number of plates, the parallelism that you have, the number of requests that you can make in parallel. And so when you're thinking about the high volume stack, you should be thinking in terms of the parallelism. And by default, it's about, I think it's 20. That's one of the numbers I'm going to get wrong. Check the documentation. But it's about 20 requests that you can make at the same time. And if you're making those requests very, very quickly, and they're super fast to complete, maybe the rate is what's limiting you, but often that's not the case. Often you're making 20 requests, and they take 10 seconds each to complete. And what would double your speed is to have more parallelism, more requests working together at the same time. So hopefully that helps to know what to ask for when you're asking for Earth Engine uplift. All right, I'm doing BigQuery. We're going to go real quick. My main job here is to tell you what BigQuery is. If you haven't heard of it, can I get a show of hands? Who's used BigQuery? Wow, nice, awesome. I don't need to do this. It's like Earth Engine, but for vectors, is a fine one-sentence pitch. It scales. There's a great data catalog. You interact. You describe the processing that you want to have happen. And BigQuery works at scale with geometries and tables to do that in a large and scalable way. Virtually unlimited resources. They really mean it when they say it. The fabulous thing about BigQuery, for me, is the surface area. So the number of things that BigQuery reads from and the number of things that it talks to, or the number of things that read it. So I use some logos here. I'd be hard-pressed to tell you what exactly those bottom four are. But there are a number of tools that push data into BigQuery and a number of tools that pull out of it. Many of them that pull out of it are not even tools that Google built or Google owns. These are just other third-party tools. BigQuery is this, the lingua franca of moving vector data around. So there's this really fantastic structure. It complements Earth Engine very nicely, and it has that great surface area that we can work with and we can use to connect Earth Engine data, push it into BigQuery, and then that opens up a lot of doors for us to be able to use our formerly Earth Engine data with many, many other tools and many other use cases, many other shapes of processing. I will talk just a bit. This is really what it used to be like. We were excited to announce a couple months ago a simplification. You used to have to juggle data to get it into BigQuery. That's not the case today. It just goes directly in with this export to BigQuery call. We're really proud of it. We hope that you try it out. We are also really excited to share this demo. If you go, the important bit of this slide is that link. Please take a picture, memorize it, write it down. Oh, not that link, sorry, the other link. I mean, write that one down too, but there's a great blog post that talks about using BigQuery for detecting flooded roads. And it highlights the strengths of Earth Engine to find floods and the strengths of BigQuery with large vector processing capabilities to identify flooded road segments. This is the link I wanted to share with you in particular. This is doing that blog post, recapitulating that whole series of processing steps in an environment called Qwiklabs, which it gives you an environment, a little contained environment that you can run in for an hour. And it's really nice because you pay, I think it's $1, a US dollar, to access the Qwiklab. It doesn't generate any charges or costs outside of it. And it's completely self-contained, so you can't risk messing up or setting up configuration. that will persist and be confusing. It builds an environment and then tears it down. It's a nice educational tool. We're excited to share it with you. If you want credits for Qwiklabs, talk to somebody here. I don't control it. Find somebody else. Yeah, so that's Qwiklabs. We're excited to talk about that. Please try it out. Give us feedback. Let us know what else you'd like to see there. There are some details about BigQuery. We're running out of time here. Just know that there are some limitations because it's that managed service, that batch task that's pushing data from one system into another. Just be aware that there are some limitations, both baked into BigQuery, like this maximum row size, as well as some that are from the Earth Engine side. So the number of vertices that you can export into a geometry is a setting that you can control, as well as the error margin for reprojecting data. You can do this manually today. We're going to make it a parameter in the future. And then just a note that this big batch task usually operates serially. If you want to really, really squeeze performance out and move a lot of data into BigQuery, sometimes your best option is to use the high volume API to juggle those data. So manually parallelizing will let you go much faster. This is the motorcycle analogy, but it's a little harder to operate. All right, with that, pass over to Alex. Thanks all.
Thanks so much, Michael. I'm Alex again. I work in Google Research. I work on weather research. A lot of my task is using all the APIs that the great people on the Earth Engine team have built to work to load hundreds of terabytes, maybe up to petabytes, into Earth Engine and out of it for the purpose of building weather models. To do this, I've built, my team and I have built a couple of power tools to make this a bit easier. The first of these two tools is called Weather Tools, or Google Weather Tools. And just as a kind of a brief demo of it, or kind of like this is the experience of Weather Tools and what it is. Weather Tools are a set of Apache Beam pipelines, so they run on Dataflow, and their goal is to make weather and geo datasets accessible and useful. Kind of the design of the tools are in mind such that they're designed for scientists who'd rather focus on science and not data engineering. So you can git clone the repo and install it with Conda, and then it's a single command line invocation, weather move EE to load data into Earth Engine. To do this reasonably fast, to meet our research use cases, we actually do a lot of, what the bulk of this tool does is it transforms data into COGEE and uses the external storage APIs that my colleagues have just spoken about today. And then instantly, or pretty fast, your data is available in Earth Engine via external storage. It's really great to build on top of these APIs. My team and I have loaded over, let's say, of 100 data sets into Earth Engine to do climate and weather-related research. One thing I really like about Weather Tools is that it supports subscribing to data. If you have data appearing in buckets, let's say like a forecast that regularly disseminates, you can just add a pub subtopic and automatically ingest data into Earth Engine in a streaming processing fashion. We can load data sets like her into Earth Engine in under 5 minutes per each new example. Her has about 100 bands or something like that, so it's a pretty extreme data set to be able to cover. Another use case that I'll mention, there's been a lot of excitement around BigQuery at this conference. And one thing that Weather Move can do as well is it can load raster data sets as point data into BigQuery. What's exciting about this is kind of an experimental model, but other parts of cloud outside of Earth Engine have proven to themselves to be a really great geospatial database. They have really great analysis tools and ways of querying data. I mean, SQL still reigns true as the most democratized language out there. With Weather Move BQ, you can take data that's in NetCDF or GRIB format and load it as tables into BigQuery. What's really exciting about this too, we've used Earth Engine's export system with Weather Move BigQuery to automatically export data from TIFFs and then pipe them into BigQuery as tables, and then able to do certain types of queries that for machine learning use cases to be able to arbitrarily select different variables using kind of the power of both systems really, really well. I guess my one caveat for this is more of an experimental kind of feature, but it's really useful. It's just quite expensive. You do get the power of BigQuery as a execution engine for doing geospatial analysis, but Earth Engine is more efficient. It's more efficient to have information kind of compact together in a raster. That's a brief summary of weather tools. There's other capabilities that it offers. I also want to talk primarily about getting data out of Earth Engine, a tool that we've built, actually released less than a week ago, is called Xee. To explain Xee, though, I want to give a bit of background. Kind of the Xee is, the short-term title of it is a extension for an XArray extension for Google Earth Engine, but that kind of begs the question, what is XArray? From just polling the audience, how many people here are familiar with XArray by show of hands? Okay, quite a lot of folks. I'm really happy to hear that. But let me just give, if anything, you'll please indulge me in a brief history lesson at the kind of the founding principles of XArray and how it fits in with the scientific Python ecosystem. So first, I'd like to talk about NumPy. In the beginning, there was NumPy, and NumPy, it's like a low-level linear algebra library. It lets you do matrix algebra in Python. And one of the innovations of NumPy is that in Python, this would be really efficient to do standard. What NumPy does is it has really efficient C binaries or even Fortran like LAPACK, and it expresses matrices as one large continuous array, and then NumPy does the work of centralizing all the manipulations of references. So in Python, you can actually think in terms of matrices and large ND tensors, but in reality, you're actually doing really efficient operations on this long contiguous array. And NumPy really is one of the lingua franca libraries of scientific Python. And it's really, really great. It's revolutionized scientific computing, and it's really good, especially in its idiomatic in Python. It's really good for abstracting linear algebra, in a Pythonic way to get the most performance you can get out of a single CPU. And then there are other great languages in data science. R is one of them. They natively have a panel data structure built into the language. A lot of people in the Python ecosystem really wanted to kind of express. Have a really more convenient way of manipulating and expressing, doing operations on tabular data. NumPy, it doesn't really work that well for this. There's not really good. Traditionally, there haven't been really good labels on the dimensions of ND tensors, and there's a lot of essential operations that you can express really easily that are SQL-like, that R has built in that didn't exist in Python, and so Pandas was created. Pandas is short for I think like panel data structure, what's really great about Pandas is it's built on NumPy, and it adds really core components to the ecosystem, such as metadata, like labels on dimensions, and this kind of fluent interface you can see here. You can read a CSV and kind of in a fluent expression, just use pipe different operations on top of it, and then its method chaining interface is a really powerful expression medium, and that's really great. Pandas gives equivalent to SQL-like capability for data in memory on a single CPU, and that's been a huge benefit to the Python ecosystem. But there's kind of still a problem with this, is that NumPy and Pandas data frames are great for working with data, but what if you want to work with datasets that are larger than that can fit on a single CPU with the memory resources of like a laptop or even a single machine? This is really common in the case for geospatial data sets that we all would love to work with. Data often that you would download and work on even a really beefy machine is too big to be loaded into the environment where you'd like to process it. Dask came in and really solved this problem really well. It lets you, it splits up kind of computation that you would do into a graph of tasks, and then you can schedule it, you can distribute it on make the most of the resources you have available to a single machine, and it even it has been extended, that same model, to use all the resources available to even a data center. People are creating clusters on top of Dask. I think maybe the best feature of Dask is that it has, it's basically a drop-in replacement to all our favorite libraries in Python. Like, you can import Pandas as PD, you can import Dask data frames as PD. Same with NumPy, you can import the data array and you have the same sort of interface. And hidden to you, but under the hood, you have a really powerful parallel processing system in Python. And that's really excellent. I think that's what's so great about Dask, and it's done really wonderful things in the ecosystem. The way Dask works, kind of a core concept of this is this idea of chunks, that in order to work with data bigger than you have to process it, you break up the large data sets into small little bits, and you stream them in from wherever they're located just in time to be able to process it. And on top of that, operations are evaluated lazily. So you can schedule a bunch of work to be done, and only when you need to download it or actually hit load, df.load, will you actually execute all the operations and do the more expensive type of compute, which is really great. If you listen to, I think Mike Dixon's talk yesterday, you can see a lot of parallels here about how this operates. In that, you can do things like, kind of the same lessons that work in Earth Engine really apply to Dask. But maybe I'll leave that as a topic for another talk. So I guess I want to ask, what if you somehow combined NumPy and Pandas and Dask? What would that look like? NumPy, Pandas doesn't really have labeled axes and metadata, and it's not parallel. And you might want to work with ND tensors. This is more or less what XArray is. Just talking about the data model a little bit, this is kind of the illustration of what a XArray data set is. This is a good visualization that I think of often. You kind of have it really is, if you've seen the netcdf, the TLDR of XArray is it's a Python in-memory netcdf. The way it works is that you have, I come from a machine learning background, so I think of it as you can have, you have an image with color channels, but you can have 100 or so, or as many as you want color channels, as opposed to 3. So the variables, they're similar. Well, they're the different color channels, or they're the variable. They're data that you have that are densely packed arrays, they're rasters. They're organized along dimensions. In geospatial data, it's usually lat, long, and time. And then you have other coordinates that also define other metadata on top of the dimensions. And each of these things, they have attributes. You can add other metadata, like just a Python dictionary on top of whatever you want. So you can keep track of all the context for the data that you have. This is what it looks like. This is the intro data set that you have in XArray. You can load an air temperature data set. This is what you get if you print it in a notebook. You have lat, long, time, and then you have a single data variable air, and it has attributes. That's the metadata that I was talking about. So just as a background, who uses XArray? I think the audience is really familiar with this. It's a very popular project and a core tool for geosciences. But I want to ask you a question what is an XArray dataset really in terms of Earth Engine concepts, in terms of an image or an image collection? Well, if you kind of examine it further, lat and long are these core coordinates. For datasets that you typically you see, they're basically kind of like x and y dimensions on an image, like an image height and image width. Time, maybe we can abstract that to be similar to an index in a collection. Usually indexes in Earth Engine image collections, they have a time and a property element. Band, data variables, they're basically bands. So isn't this an XArray dataset basically just an EE image collection? And my answer to that to you is yes, it is. And that, in a nutshell, is what XEE is about. XEE basically attempts to use the XArray data model with all of the deferred computation, streaming, metadata labeled on XArray datasets, fill the missing hole in the Python ecosystem, but using data in Earth Engine as a backend. So this is the time that I'd now like to do my demo of what this actually looks like in practice. So we install XEE. It was pre-installed. We can then initialize Earth Engine and make a connection. We're using the high volume API, as Michael spoke about. And then this is what it's like to get Air5 land. I think since the 80s is the data set all the way up to the present. It takes maybe about 30 seconds to load because we're having to collect the information, the metadata about every single point in time from Earth Engine. And I'll stage up what the data set looks like. Just some characteristics about this load time, and also not to have dead air because no one likes that. A lot of XArray really is traditionally built around XAR as a use case, And I think it's really interesting in talking to the creator of XArray, Stefan Hoyer, who uses Xar quite a bit. The characteristics of this type of time, spending 30 seconds to open a large Earth Engine data set, actually very similar to opening a large Xar data set. They kind of have to do the same kind of network operations under the hood. So you can see here, we have a large number of time points. That's why it took maybe quite a while to open. Here are all the Era5 land variables in an XArray data set. And it has attributes. This is metadata that I pulled from the get info call of an Earth Engine collection. There's a lot of HTML here. I feel like we could do a better job at rendering the HTML. That would be nice for me anyway. And then so then you can use Earth Engine, so XArray operations. You can use cell to get like particular points in time from the Earth Engine collection. Here's 24 hours of Halloween on land. You can plot data as if it's just like any other XArray data set. Maybe not today. Let's see, did I not? OK, so we have an XArray data set. This is the very fun part of a live demo. I maybe would, I didn't install matplotlib. That's a classic type thing. This is not my home environment, but you'd have to take my word that matplotlib would, if I had it installed, it would plot. Let's see. We can pip install, if we have netcdf4. So maybe this is the really exciting part of for the title of the talk, getting data out of Earth Engine. We can use built-in XArrays. You can see here it appeared. We can get just call to netcdf on the XArray data set on a sufficiently small slice of data, and then it really is openable from XArray as well. So this is like maybe, hopefully kind of a game changer in how we think about getting small slices of data. If you're not an XArray fan and you like TIFFs, you can get XRaster.io and Raster.io to, if you have those dependencies installed, which I don't think I have, you can get TIFFs just basically with the same process. And then what I think maybe one of the killer features, and this is maybe an important distinction in like where the boundaries are drawn, is that you can pass in not just a path, but you can pass in a processed image collection. So that all the stuff that Mike Dixon was talking about yesterday about how to efficiently pre-process things on the back end of Earth Engine, all available to you. You basically get the best of both worlds. You can do stuff kind of streaming on Dask client side using XArray and Xee, and you also can use the full power of Earth Engine as a planetary computer. Just by using the native Python interface and doing filter operations. So this Halloween's, for lack of a creative naming, you can see it's fewer time dimensions because we've done the filtering Earth Engine side before doing it here. Thank you. I'd like to return back to my slides. The one last thing I'd like to leave you with is that Xee and XArray integrates rest of the XArray community or like ecosystem. So it integrates, for instance, with XArray Beam. And I guess why that's interesting to you is this 25 lines of code, it's in the examples in Xee, is all that I had to write to load 20 terabytes of NASA iMerge data into Xar. And I did it in about 3 hours on like internal infrastructure. We're trying to make the data flow example work. No really messing with quota or waiting on a task system or anything like that. I'm really excited, I guess, about what kind of this one ecosystem, hole to fill means about the scientific Python ecosystem, and what I'm really excited to see what you all will build with it. With that, thank you very much for your time and attention. Happy to go into questions, and thank you to the other speakers. Have a good day.
So I don't know whose mic is on, but if you want to if you have questions, if you want to step up to the microphones, and please line up right behind a mic.
Hi, thank you for that presentation. I have a question about Xee. So if I understand correctly, you have to call an image collection for that to work, right?
It only works in image collections, not feature collections.
OK.
But support, that's an area of interest for our team to explore. OK,
and can the images be array images or just regular images?
I haven't tried array images. I would love to, if it doesn't work on that case, I bet it's something we'd like to support.
OK, great, thanks.
Ports.
Yeah.
Question for the last speaker. Thank you for that. So based on your examples, it would seem that you don't have to worry about the 32 megabyte sort of limit per chunks. It just does all that for you. You can specify a large AOI and it just takes care of that.
Yeah, really glad you asked. I just pushed this feature yesterday, automatic optimal I/O chunking. So there's two types of chunks you have to worry about. You have to worry about the chunks for Dask to do the computation efficient. I have a separate set of chunks I call I/O chunks that are dividing up the Earth Engine request into little bits and then reassembling them. By default, I calculate, based on the dimensions of the data, how to get as many as possible, all 48 megabytes per request. And then you can also override that if you know better than me about how you should structure the chunks. Because sometimes, I make a guess, but sometimes you want to get a certain dimension more than the other. But that is left, it's similar to the Dask model or the XArray model of chunks. But it's an important distinction between the I/O and the CPU-bound computation. There are two types of chunks for each of those cases.
So that capability is built into the library?
That's right.
Okay, thank you. You're my new hero. Thanks.
Thank you.
I also have a question about XEE. How do you control the resolution in CRS that you're getting data out of?
Love that question. You can use a CRS string, a WKT string, which goes into the Earth Engine projection backend. And if you rather work in Earth Engine concepts, you can pass it an EE projection object.
So you do that while it's still an image collection and then pass it into an XArray dataset?
Yes, you could do either. Well, here's the thing. When you do the open dataset call, we open it in a projection. So if you're doing it, we open the open call in order to get data naturally in Earth Engine might be a very different resolution to projections. We have to coalesce them into the same representation upon open. So if you do it on the Earth Engine collection raw, you need to get the projection from the image collection, and then pass that in as an argument to the open dataset call.
And if you want to use a resampler, how would you do that?
I'm about to write that documentation, but yes, that's a use case that we definitely want to support. And I need to learn more about the Earth Engine concepts. I'm thinking, I do this more like in Python and Beam, and I want to see what I get for free with Earth Engine to make those two things work. So I don't know the answer to that. Maybe my colleagues here would be a better answer, but we'll have that documented soon, because I had another researcher I work with who wanted that immediately.
Cool, I might email you.
Yeah, please do.
I was just going to add that since you can pass Earth Engine objects to this call, theoretically you can pass a resampled image directly, because you can use .filter, .resample directly to this XEE. So theoretically you can do the resampling in Earth Engine and then call that and then do export if you want.
I think that is how it would work.
Okay.
Yeah.
Yeah, amazing. Well, I'm also very excited about XEE. So I yesterday already contributed a couple pull requests. And,
Thank you.
But just to give you a break, I will ask questions other speakers. So Sam did the tool that allows you to raise the images through a bucket to that. I was wondering about vector data. So right now I'm doing, for example, I have a vector file, 20 gigabyte.
Yeah.
What's the recommended way of getting that into Earth Engine?
Yeah, you can. Well, technically, okay, yes and no, because I don't actually know if it will allow you to exceed that limitation that it has for shapefiles, and this file still has to be a shapefile format. So the 2 gigabyte limit that's imposed by shapefile is still relevant in terms of vector land. So I don't think there's a way to bypass that, unfortunately, even for shapefiles or objects in vector, unless, Michael, you have a different answer. No.
Shapefiles have that limit baked in.
So basically you need to subdivide into smaller pieces? And
yeah, you can subdivide and then flatten. Put everything in folder and read the whole folder and then flatten it. And then you will get one uniform feature collection.
Yeah, I was wondering that it would be great to have some of those in documentation, because you have tons of watershed dataset and other sensors like rows dataset. Rows, I believe, there's many gigabytes, not like 2 gigabytes.
So yeah, I have
interested in getting large vector data into Earth Engine.
100%. So I have tools that I use for ingestion and chunking of shapefiles. Just like Alex released this weekend, I also released COGEE this week. So it's going to get more mature. I'm going to add more documentation. But yeah, I like that idea, because right now it can only do raster. But I'll add some documentation and docs for documentation for features. Yeah.
Awesome, thank you very much. So
Yep.
COGEE, maybe have another one like ParQE or whatever, like can get it into Earth Engine.
I love it. Yeah.
Yeah, I'm gonna go back to the XE, and I have a question. If you're planning to have an implementation like the preprocessor, like the XArray has, before loading the data, we can do any processing on the raw data before loading it.
If it's part of the XArray model, I think does Open Dataset have a callback? There's like preprocess.
Yeah, so when you do like opening, you can do preprocess, adding an extra dimension or something like that.
I don't see why that wouldn't work today. It's the Earth Engine. Earth Engine has a really it's beautifully extensible. Where like you just implement the backend and you get so many things for free. I haven't tried it, but if it doesn't work, we'll patch the bug. But it might just work right now for free. Also, I didn't demo this, but OpenMF Dataset, you get that for free too. So you can if you have to limit the number of images kind of up front to be the same. But you could like my documentation. I need to fix a bug, but yeah, you can like open multiple datasets. So there's a use case we have, for instance, is we have a lot of we load pressure level data for weather forecasts into one image collection each, but we'd like to think of them, the atmospheric levels as just different data variables. It's just an MF dataset call, an XArray, and it all just works.
Yeah, I think that's a great example when it comes to, for example, opening multiple files, but they have the same variable name, so you want to change the variable name before opening them. That's where the preprocessor comes into play, that you can do that before opening them and combine them as a same dataset.
Awesome. I would love to see it in practice. I don't know if I've hit that use case in my work yet, but I would love to see it shine in this instance.
I also wonder if you can do an internal join and then pass it as a pre-computed Earth Engine object, because then you'll have two collections joined already, and you can pass like two separate variable names if you wanted to.
Yeah.
That might also work.
Perfect.
Just something
Thanks
to try,
so
I
much.
guess. Yeah.
Super. We're at time. Thanks all.
Thank you.
Thank you, everyone.